Welcome everyone to the Deep Learning for Microscopy course. Before we get started with the actual content of the course, we want to give you some introduction to the basics of these topics. Right, so the goal of the course will be to learn how we can use deep learning algorithm for image analysis problem, specifically in microscopy, but the things you will learn in the course will also be useful for other tasks. But in order for you to understand these topics, we have to cover some basics. And today, right, we start with the basics of machine learning. Machine learning is kind of the basic field from which deep learning derives. And then in two other lectures, we will also talk about image analysis. And then we will see how we combine image analysis with machine learning. But yeah, for now, let's get started with machine learning to discuss what this actually is. And the idea behind machine learning is to teach computers how to make decisions for new data. And to motivate this a bit, so what we want to do is to solve automatically tasks with a computer or with an algorithm. And we can also cast this as sort of the problem of making decisions for new data. Right? So we have some data we want to analyze automatically, and we want to make decisions with an algorithm, with a program for this data. And we will see a lot of more concrete examples of this in these lectures, and you will work on them in the course. But to discuss this on a high level first, right, for these problems, we have two different approaches. The one is normal programming, where we work with predefined rules. Right? So basically, we analyze the data and we see what sort of condition is fulfilled by the data, right? So be this condition A, condition B, and so on. And then we take our decision based on which condition is fulfilled, right? If A, then we do X. If B, we do Y, and so on. Right? So this is the one approach. And this works well if we can define clear rules. But often defining clear rules is not really possible. So this is where machine learning comes to the rescue, where the idea in machine learning is to learn the decisions from example data with known answers. And as we will see, this is very helpful in a lot of problems where we cannot define clear rules. Yeah, let's make this a bit more concrete. And first, let's talk about the normal programming case, because of course there are a lot of problems where this rule-based design works quite well. Right? Let's start with a very simple problem of saying that you are giving a date of the year and you want to say which season this is. Right? So for example, we give the date 1st of November, right? And then we can immediately say this is in the fall. Right? And if you write this down as a program, it's pretty simple to determine the date range and then sort of associate each date range with the season. Right? So this is a clear case for a problem where normal programming works really well. Right? And there are, of course, also more complex problems, right? Like determining the distance between points on the map, right? As you see right on the right-hand side, things you do in a navigation program where normal programming works quite well. Right? Although the algorithm for this would be a bit more complex than the date to season example, right? We can still write down sort of an algorithm, which means kind of a step-by-step solution that's defined by clear rules from the data to solve this. Right? So these kinds of problems, we use normal programming. We don't need machine learning to deal with these. But there are many other problems where defining these clear rules is very hard or may even be impossible. And this is where we use machine learning and where our goal is to learn the decisions and to implicitly learn the rules from the data instead. So let's also give an example for this. Right? Let's say you're giving images of furniture, right? Like the image of the chair over here. And the task is to classify the type of furniture in the image. Right? Is it a chair? Is it a stool? Is it a sofa? And so on. Now, how would this work, right, if we want to do this with clear rules? Right? So if you want to define rules for what makes up a chair, right, you might start with composing it into its parts. Right? For example, does it have 4 legs? Does it have a seat? Does it have a backrest? Right? You could define these as the criteria for a chair. And then you could say, okay, I try to analyze the image to find these component parts. And if all of them are there, then I say it's a chair in this image. Right? So basically make the decision based on these rules. However, in reality, we immediately see that this approach doesn't really work because there are many chairs that don't conform to this criteria, right? So this thing over here, we would call it a chair, but it doesn't have 4 legs. Also, these gaming chairs here, right, they just have a single leg that then branches out into wheels and so on. Right? So we could now, of course, try to amend the rules to also account for these cases, but you already see that this gets quite complicated. And then this is even further complicated by the fact that we can take photos from different viewpoints. We can have occlusions in there and so on. So even for objects that do adhere to these rules, we might not be able to just see the legs of the chair and so on in the image. Right? So overall, defining these kind of rules for classifying objects in images is hopeless for most complex cases. And this is why we turn to machine learning instead. Right? And the idea there is that the first thing we need to do is to gather our data with examples. So this means we gather a lot of images, right, of chairs, of stools, of tables, and possibly of other furniture. And we also need labels. So this means for each of the images in the category here on top, we know that this is a chair. And so basically someone went through and labeled all these images. For the ones that are a chair, says it's a chair. The same for stool, right? For all of them, we know it's a stool. And for all of these, we know that this is a table and so on. And then we use this data to train our machine learning model that implicitly learns to map the input images, right? So the images here to the labels, right? So to the classification task we want to solve for the images. And we will see how this actually works in a second. And then after this training, we then have our model and can apply it to new data, right? So let's say you get this image now and you want to automatically process it. So you can apply the model to it, and if it was trained correctly, it should then give you the correct answer that you're looking at a chair. Right? So this is the main idea behind machine learning, right? To learn from the data here, right, where we have these annotations, and these annotations have to be collected by humans usually, right? So we sort of have this knowledge from example here, but then once we've trained it, we can apply it to new data where we don't have the labels, and then if everything went correct, we get the correct answer. So this is the principle behind machine learning. And now let's discuss a bit more how this actually works, right? So before we get into the details of machine learning algorithm, let's formalize the inputs or what our training data is a bit more, right? So if we look at training data, the first thing we have is our inputs or our features. And so these are, in this very simple case, we see on the left-hand side here, these points that we have, which are located in 2 dimensions, right? So we have 2 axes here, the x1 axis and the x2 axis, and each point here corresponds to sort of one sample or one data point, which is characterized by the 2 coordinates x1 and x2. And this is now a very simple example, but you could also think about each of these points being one of the images we've seen before. But here now, to understand things better, we just deal with these 2D input points. And then we also need these labels or annotations, right? What were our furniture categories before? Now, to keep it simple here, let's just say we have 2 categories. Category A, right, which are all the points over here, and category B, which are the points down here. And again, we somehow get these labels either from some human annotation or some other source, but for the training data, when we know for each of the points what the category is. And so this setting we call supervised learning, basically because we, for our training data, know all of our categories or our labels. And the goal now with the machine learning algorithm is to find the best split between our categories. And I mean, we often call this a decision surface, which is a bit of a fancy word, but it just means sort of to find some boundary between these 2 categories, right? So in our simple case here, this boundary is this line, right? So the line you saw here, we see that if we can find this, all the points of category A would be on top of this line, and all the points of category B would be below this line. And if we have a more complex problem, then we may need something more complex in a simple line. But the idea in machine learning is always kind of the same, right? We try to or we have the data given in some input space. Here it's very simple and two-dimensional. It could also be more dimension. And then we try to find this decision surface, so the boundary between our categories that best separates this data. And after we have found this separating surface, we can then put new data into this, and we find sort of where it lies with respect to this decision surface, and we categorize it based on this. So this is a very high-level idea, and we'll see in a second how this works more practically for some example machine learning models. Before this, just to say that there are also other machine learning approaches. One is unsupervised learning, where we actually don't know our categories beforehand, and then we can try to cluster the data without this category knowledge or to reduce the dimensions. And then other approaches are also reinforcement learning, where we train an agent to interact with an environment. This is very relevant for robotics or to play games. We will not deal with this in this course much, but I just wanted to mention this for completeness. Now going back to our supervised learning case, we have two main tasks in there. The one is classification, which is what we've discussed so far, right, to predict categories based on the features or based on our input data. Right? So we have our data points, and then we have a number of categories, either 2 or more, and we want to sort of classify our data into these categories. One example would be to classify objects in images, similar to what we've seen with the furniture already. The other would be, for example, to classify the phenotype of a cell from morphology features. And the other problem is regression. Right? So in the case of regression, we are not predicting these discrete categories, but instead we predict a value based on the features. Right? So a good example for this would be to predict the price of a house based on its size and its location, and may also be other features. But right, the price is sort of a continuous value, right, ranging from, 100,000 to $1 million or euros, and it's not a simple category. So again, just mentioned for completeness, we'll focus on classification for now, and also the models for regression are pretty similar to classification, but I just wanted to make clear that there's these two different formulations that we deal with in supervised learning. Yeah, and now let's really come to a concrete machine learning model that we can use to classify our data. And the question that we ask here is, like, how do we model this decision surface, which is in this pretty simple example that we looked at, just a line, right? So how can we parameterize this line, and then how can we find the parameters of the line that best separate our data? What we also do now, just for simplicity, is we associate a number with each of our categories, right? So category A, we just say corresponds to the number 0, and category B corresponds to the number 1. And then we go on to the perceptron, which is a bit of a fancy name, but it's a very simple machine learning model that is just parameterized by two weights. And I'll first go through this diagram here that shows this model, and then we explain how it actually works over the next slides. But the idea behind this perceptron is that we have two weights, W1 and W2, and each of these weights is associated with our dimensions, right? So W1 is associated with the first dimension, right? So x1, and W2 is associated with the second dimension, x2. And so if we have one data point here, right, we have some x1 value and some x2 value. So what we just do when we apply the perceptron is we multiply the weight W1 with the value for x1, and we multiply W2 with x2, and then we take the sum. Right, so this gives us a single number, which is W1 x1 plus W2 x2, and then we take the threshold of this, and we classify the data point based on this threshold. Yeah, so and we see now why this can solve our classification problem over the next few slides, looking at all these components in a bit more detail. Right, so the first thing is what do these weights correspond to, right? This W1 and W2. So these give us the direction and location of our decision surface, which again is just a line here. And in particular, they tell us the normal vector of the decision surface, right? So the W right, it gives us basically this vector here, and it gives us this direction, and this vector is the normal of the decision surface, right? So the normal vector just means that this is perpendicular to the decision surface here, right? So I mean, you see this visually quite well, right? This is perpendicular orthogonal to this vector here, and the direction of this vector W is parameterized by these two values, right? The 1 is the direction into the x1 axis, and the -1 is the direction into the x2 axis, and we see that this corresponds to this vector here, and our decision surface is perpendicular to it. And if we were to move the W vector, or try to change its direction, right? For example, if we would move it up to here, right, then also our decision surface would change. So this is how we parameterize kind of this boundary between the two classes in this perceptron model, right, with these two parameters, or more generally with one parameter per dimension, these weights. Okay, right, and now what we do, as we already said, when we apply this to a data point, is we take the x values, multiply them with the weight values, and then take the sum. And there's a pretty easy interpretation of the value that comes out then, right? Sort of the summed up value here. And this is just the distance to our decision surface, right? So if we take one of these points here, take the product with the weights, and then sum all of this up, the value that it gives us is just the distance to the decision surface. And it's the distance along this weight direction, right? So if we do this now for all of the points, right, for each point in our plane, we compute this weighted sum, right? We see that we get our distance of the points to the decision surface, right? So this is the distance 0 here, right? So this would basically be points that lie directly on this decision surface. And then if we go to the left here, right, these are points that are basically up here, sort of far from the decision surface. And the closer we get, sort of the smaller the distance gets, but all the distances here are negative. This is just because of the direction of our weight vector. And the points here, right, they correspond to the positive distances down here, right? And the further we get here in this direction, the further out we are here in the distance to the decision surface, right? So in summary, this means if we now apply this weighted sum to one of the points, we measure the distance to our decision surface. And then we can pretty easily see how we can use this to categorize our data, right? We can just say that everything here to the left of our decision surface, this is category A, or the blue category, and everything to the right is category B, or the red category. And this means in order to classify the data, we now just need to threshold these distances, right? We say everything smaller than 0 gets the value 0. Remember, we associated this with the blue category, and everything to the right of the threshold, so everything bigger than 0, gets the value 1, right? Remember, 1 was the red category. And now we see how, sort of, given this pretty simple model, we can classify this problem into two different classes. Yeah. So we can also see now, right, if we have a new data point, that all of this still works, right? Let's say we are given this yellow point here. Say it has the x coordinate, x1 coordinate -1, and the x2 coordinate 2, right? This roughly corresponds to the position of this point in the plane. Then if we sum this up with the weights, we get a value of -3. We see that this is smaller than 0, so we predict category A, right? Just following what we discussed on the slide before. And this is, of course, the correct category for this point, given its position, right? So we see is that if we have these weights, we can apply it to new points and automatically make these decisions without knowing the category labels. What we haven't talked about so far is how we actually find these weights, right? So this is really the crux of the machine learning part, that given sort of the data with annotations, meaning all these points here and here, where we know our category labels, we determine this value for the weight vectors that then give us the position or the direction of our decision surface. And we will not talk about this in much detail for this problem, But there's this perceptron learning algorithm that basically fits these weights for new data where we know the category, and it finds a separating line that best separates two classes, okay, and also be multiple classes. And this is kind of the whole trick in machine learning, to come up with these algorithms that find parameters. Again, in this case, the parameters are these weight values that give us the best classification. And so this was, of course, a very, very simple example, just with two classes and two dimensions, but all of this also works for more complex scenarios. So let's look at a bit more complex problem now, right? Let's say we again have our two categories, but now they are sort of distributed like this, right? We have the blue category here, and the red category here and here. So can we apply the perceptron that we just discussed also to this problem? And this question boils down to, can we separate these categories now with a single line? Right? Can we put in a line like this that separates all the categories, or a line like this that separates them? And I mean, the clear answer is no, right? So the way these classes are positioned, we cannot just separate them all with a single line, right? I mean, you can maybe go through a few more lines in your head, but you will clearly see, right, that it's not possible to do this with a single line, right? And like here, we will always have points of one of both categories on these two sides of the line with this, right? So for this bit more complex problem, the pretty simple linear model, so perceptron, that we just discussed, does not work anymore. But of course, we can turn to more complex models that then actually can also solve these more complex tasks with data. And this brings us to our second example, which is a decision tree, right? And so this is a bit more complex model that now allows us to separate data in as we have it here. And the way this works is to hierarchically separate our input or our feature space into regions. And we always sort of at each level of the decision tree separate our input into two regions, right? So let's start here at the first level. So for example, right, we can separate the data into a region that where x1 is smaller than 0, right? So this would be this region, and the region where x1 is bigger than 0, right? So this would be this region, right? So this is sort of the first level where we kind of put all the data that's to the left into this branch of the tree, and all the data that is here to the right into this branch of the tree, right? And now we see that we've separated our data a bit, but of course we still cannot put each category or each category into a single part of this tree, right? So what we want is sort of that we have these sort of buckets or nodes here in the tree, which correspond to some region in our feature space, and all data of one category should end up basically just in a single node here of the tree. And we see that with one split or one level of hierarchy, that does not work yet. And of course, this would still correspond just to a single line that splits the data, right? This would be this line now that splits it. But what we can do now with the decision tree is further split the data by adding more levels to the tree, right? So we can go sort of here to kind of this left node that we had, and then we can also split this node again into two regions, right? So one region would be where x2 is now smaller than 0, right? So this would be this region of our feature space, and the other region would be where x2 is larger than 0, right? So that would be this region here. And we can do the same on the right-hand side, right? Ending up sort of with this region down here and the region up here corresponding to this branch. And now we see that we separated our data or our input or feature space into 4 different regions. And these regions now allow us to separate our categories correctly, right? We just have to associate sort of this node of the tree. We also call it the leaf because this is where the tree ends. And this leaf here, right, corresponding to these two regions with the category B, and vice versa, right? We associate these two leaves of the tree, which correspond to these two regions, which category A, right? And now with this more hierarchical design, we can actually distinguish or separate these categories from each other. And again, if we apply this to new data, right? So if we have a new data point that comes in here, we can sort of walk through the tree and get our classification. So this means, right, we start here on top of the tree, we put in the coordinates of this data point, right? For example, this could be here x1 equals 1, x2 equals -1. And then we look at the first decision here, right? Where do we land, right? And sort of the question here is if x1 is bigger than 0, which is the case, right? Then we go to the right. And then we are here at this decision. We ask if x2 is smaller than 0 and go to the left. And then we end up right in this region here, which is associated with category 1. So we see that this decision tree sort of works for new data. For each data point, we can walk through the tree and we get our classification and ideally get the correct result. And again, we haven't really talked about how we learn the decision tree, and this is a bit more complex, so we'll also not discuss this here really, but just to say that we again can parameterize this tree, right? Similar to the weights that we had in our earlier perceptron model, we have now parameters here in the tree, which are kind of these threshold here for the splits, right? So remember we said in this first level, we split the data into two regions, one that's where x1 is smaller than 0, the other where x1 is bigger than 0. And so the parameter here would be sort of this value for the split, right? It doesn't have to be 0. It could also be some other value, and this would move sort of the line of the split here. And then the other parameter is also how far down we grow the tree, right? So in our example that we had, we just grew everything to 2 levels, and then the data was separated perfectly. But if we had an even more complex data distribution, right, like this one shown here, where sort of the quadrant down here is also divided into places where the data is blue and where it's red, right, then we can further split this quadrant here, right? You can basically see if we're here at this position, we can also continue splitting the room or the space and have a new threshold and say if x2 is smaller than 0.5, we split it again. And this is what we can sort of continue ad infinitum and map the very complex distributions of data to this. But yeah, this is just to say, right, so we also have parameters of this decision tree, which are the places for the splits and how long we grow the tree. And with this, we can fit most kinds of data. And the learning algorithm for the decision tree is just what gives us these parameters given annotated training data, right? So that for a given data constellation, we get our tree. So these were 2 examples of machine learning models, and we will discuss more of these in the later parts of the course, focusing on deep learning. But let's try to generalize a bit what we've discussed so far, right? So as we've already said, right, the thing we always need is our data set, right? So where the data set is basically our inputs, right? In this case here, this would be images, and then our labels, right? The known answers for these images. And these here would be, animal categories, right? And so this already means our task here is to take the image and classify it into what animal is shown in this image. So this is always kind of the starting point, that we need this data set that we use to train and evaluate the deep learning algorithm. And then given this data set, the first thing we do is we split this into a training data set, which we will use to actually train the algorithm, a validation set that we will use to validate its hyperparameters, and a test set that we use to check the performance of the algorithm for real data. So let's see what this means in a bit more detail. Right? So the next thing sort of that we need to do is training an algorithm. And this means we actually need to define what model and learning algorithm we want to take for our data. Right? This could, for example, be the decision tree we discussed, or the perceptron, the linear model. We use this training set to fit the parameters of our algorithm with, or of the model with the learning algorithm. Right? So remember, for the example of our decision tree, that would be sort of the splits we do in the tree. and the depth of the tree, and we fit these parameters so that they best classify this training data set. And then there may be additional parameters, we call them hyperparameters, that sort of are settings of the learning algorithm, for example, and we would use this validation set here to find the best settings for these parameters. And we need to use a separate set of the data for this, because we cannot trust the results we get on the training set, right? So basically, if we go through the training set and classify all the examples in there with the algorithm that was fitted on the training set, then the results there will be quite a bit better than what we get for data that was not used for training. So that's why we have this validation set to determine parameters that are not trained with our training algorithm, but rather that determine how the training algorithm works. So that's a separate validation set we have for this. And finally, we have the test set that we then use to evaluate the final model. And the goal of this is to estimate how well this model works for new data that was not used here at all in training, and also wasn't used here in order to find these good hyperparameters. Right? And this gives us an estimate, right? If you would use this model in practice to automate the task you're interested in, how well does it work? And you can judge based on this of if the quality of the model prediction is good enough or not for the task you want to solve. Yeah, and this is also really the golden rule of machine learning, right? To never train on your test set, right? So meaning the data that you use here to evaluate how well the model would work in practice may never be used here in the training set, because as soon as the model sees this data during training, we cannot trust the results anymore that we get. Yeah, so that was almost all we wanted to cover in this first lecture. Just to say that we've dealt with fairly simple models here now, right? We discussed this linear models like perceptron. There are other linear models like linear and logistic regression. Basically, these only work for data with simple relationships, right? Meaning data where we have this linear relationship between the data and the categories. We've discussed the decision trees. These already work for more complex data. And then there's also the ensemble models, right, which basically are many decision trees combined. So these are good for data where we have a good feature representation. So for example, it's just tabular data. And then finally, the models that we want to deal with most in the course are deep neural networks, right, which are used in deep learning. And these work well for data where we do not have good feature representations, which is often the case for images or for text. And we will discuss what we actually mean by what are good feature representations in later parts of the course when we discuss deep learning. Yeah, so that was everything for this lecture. This should have given you some introduction into what deep machine learning is. The most important thing here, right, is to take away the concepts, understand these, so that you know what we talk about, right, when we have a training set and a validation set and a test set, and when we talk about a learning algorithm. This is really the important thing to take away. If you didn't understand all the details, right, don't worry about this. The main goal here is to get you familiar with the basic approach behind machine learning. Yeah, we will also provide some additional reading material if you want to delve deeper into this in the video description. And in the next lecture, we will discuss the introduction to image analysis.